Welcome to Matematika. Today we're going to do 1.9 rational functions and vertical asymptotes. So, a vertical asymptote. We talked about this in my previous video about problems and solutions of rational functions and zeros. So, we'll get to know more on vertical asymptote in this video. So a vertical asymptote is a vertical line x equals a, and that the graph of a function approaches but never touches. It occurs when the denominator of the function equals 0, provided that the numerator does not equal to 0 of the same value. All right. So that means this is the reason, or this is because as the denominator approaches 0, the value of the function increases or decreases without bound. Okay, we'll get to know more on this as we move on. The multiplicity of the 0 in the denominator is greater than its multiplicity in the numerator. Then a vertical asymptote occurs. So like in this condition right here, okay, let's have these two graphs. All right. On the left side of the graph, we have f of x equals to x minus 1 times x minus 2 squared over x minus 2. If we try to see the multiplicity of x equals 2, because this means that you have x2 x minus 2. If the multiplicity is 2, that means if we equate one of them, one of the factor, we have x minus 2 equals 0, so x is equals to 2. It is greater in the numerator. That means even though we cancel out, there is still x minus 2. That means the multiplicity of x minus 2, so I'm going to write it here, multiplicity of x equals 2 is greater in numerator. That means if it is greater in the numerator, there is no asymptote. All right? Because what does it say here? If the multiplicity of the 0 in the denominator is greater than the multiplicity in the numerator, there is a vertical asymptote. But what happened here in this graph, what is greater is the multiplicity in the numerator. So there is no asymptote. So let's look at the second graph here. F of x is equal to x plus 1 times x minus 2 over x minus 2 squared. So look at the multiplicity in the denominator. So this time, the multiplicity in the denominator is greater than the multiplicity in the numerator. So when we cancel that out, there is still 1x minus 2 in the denominator. That means the multiplicity, okay, of x equals 2 is greater. Where is it greater? Numerator or denominator? It's greater in the denominator. Okay. So therefore, there is a vertical asymptote. So what is our vertical asymptote here? X equals 2. Because if we equate x minus 2 equals 0, x is equals to 2. And that is our vertical asymptote. Okay. We can describe the behavior of the function around the vertical asymptote by looking at how the function changes as it approaches the asymptote from left to right. Okay, from left to right. So in other words, we can write this using the limit notation. All right, so I say using the limit notation, we can have like limit x approaches a on the right side, approaches from the right is positive or negative. So you could say here positive infinity, or the limit as x approaches a on the left. So when you have that sign, approaches on the left is positive or negative infinity. Okay? Or equal approaches. So how do we do that? This is from the left side, or we can write the limit notation. In other words, the limit of r of x as x approaches a from right is positive or negative. From the left side, okay, the limit of r of x as x approaches a from left is positive or negative. So we're going to get to know more on writing down the limit notation of using the vertical asymptotes. Let's have this example. Consider the function s of x squared minus 4 over x squared minus 2x. Okay. So we'll set first the denominator equals to 0 and solve. So if we equate this to 0, we can still factor out x squared minus 2x as x as the common factor, and we have x minus 2. Because we are trying to get the vertical asymptote, and we can get it in the denominator. So setting it x squared minus 2x equals 0. So after factoring using the zero product property, we can have x minus x times x minus 2 equals 0. So we can have x equals 0 and x minus 2 equals 0. X would be equals to 2. These are our, we get two values of x. Before, we can say that there is a vertical asymptote at each of these value. We need to check. One way is to check. We have to check if there are not also zeros in the numerator, because if there is some holes in the function given. Okay, so if our numerator is a product, sum and difference of two terms, so we can have x plus 2 and x minus 2, right? So by looking at it, we can see that x minus 2 is common in the denominator, so we have a holes there. Setting the factors, okay? So we can see x equals 2 is 0 in both numerator and denominator. So that means there is no vertical asymptote. No vertical asymptote when at x equals 2. Okay? They cancel out. But there is a vertical asymptote. Where is that vertical asymptote? What's the other one? At x equals 0. This is our vertical asymptote. The other one, because x equals 2 is being cancelled in the numerator as x equals 2. Okay? So, even though there is not a vertical asymptote at x equals 2, there is still something special happening. Then we'll learn about this later on. Okay. Next question. Describe okay. Describe the behavior of S of x as it approaches to any vertical asymptotes. So in this part A, we found that S of x, okay, has a vertical, I have to write this down, asymptote of at x equals 0. So to describe how the function behaves near the asymptote, we can use or describe what is going on in both direction. So find the limit. We'll have to find the limit of the function as x approaches 0 from left to right of 0. This is 0 right here. What's going on the right side and what is going on the left side of 0. So by doing this, we can substitute values that are very near. I'll start with the left side. Okay? From left, we are checking the limit of the function as it approaches. Limit of the function as x approaches 0. So I'll start with, let's say, here on the left side. Let's say this is -1. I will choose like 3 numbers in between -1 and 0 and try to check. So we'll substitute like very close to 0. Like, okay, I'll do the -1 first. So what happened when I substitute it to the equation? To the function, I mean. So I have a -1 squared minus 4 over -1 squared minus 2 times -1. I'm substituting -1 to the value of x. So that means 1 minus 4, I have -1 squared is 1 minus 4. I have a -3 over 1 squared plus 2. That would be 3 also. That means the value is -1. So S of x, -1 is -1. Right? I'll move a little more closer to 0. Like in the middle, I will try 0.5. So let's say 0.5 negative. Somewhat like a little bit even more closer. So I have negative 0.5 squared minus 4 over negative 0.5 squared minus 2 times negative 0.5. So by computing, I'll get S of x, S of negative 0.5. I get a negative 3. Okay, by computing. I'll do more. One more. Very, very close this time. Let's say 0.25. S of 0.25. So 0.25 negative squared minus 4. Then negative 0.25 squared minus 2 times negative 0.25. All right, simplifying by substituting after that. When we simplify, we come up with a negative 7. I want to try it using your calculator. That's what I'm doing right now. I'm stopping and then I'm trying to compute. So we come up with a negative 7. So we can see the values are getting more negative as we approach the asymptote from left. So from left, getting more negative. Okay? From negative 1, negative 3, negative 7. As we move closer to 0, it becomes more negative. So we can write our limit notation here. Limit notation as x approach 0 from the left. So we put a negative sign there. S of x is negative infinity. Okay? So I'm going to divide because I have to think about what's going on as I do what's going on here on the right of 0. From the right of 0. So if I do the same thing, I have 0.25, 0.5, and 1. The more it is getting into a positive infinity, while here it's negative infinity. Okay? As it moves closer, if I say I substitute s to the 1, positive 1, I'm quite sure I will get a value of 3. Okay? So if I do s of 0.5, I get the value of 5 by substituting. I'm not showing it, but the same thing will come out. If I do s to 0.25, the more it is closer now to 0, I get 9. So that means it increased the more it close to 0. Okay? As we approach to 0 from right to the function, values are getting larger. This is what we mean. So we can say that the limit of the function approaching positive infinity as x approaches 0 right here from the right. Right? So we can write our limit notation of x as it approaches to 0 from right. Approach 0 from right, the function s of x is positive infinity. Okay? We'll understand more on this when we visualize what is really going to happen when we see them in a graph. Okay, let's do this first. Given the mathematical notation of the limit as x approaches 2 from right, the v of x is positive infinity. Okay, you see that? And the limit as x approaches 2 negative, the v of x is negative infinity. So the limit describes the behavior of b of x, how the b of x behave as it approaches x equals 2. Okay? X equals 2. So what is our x equals 2? That is our vertical asymptote, right? So the limit, this limit that x approaches 2 on the right side, the b of x is positive and has a positive sign, which means, okay, I'm going to write this down here. This means it is describing that the function approaching from the right side as the values approach 2 from right and v of x approach negative. So it means describing the function approaching, where does the function approaching? From the right, because it's positive, from the right side. As x values approaches 2. X values approach 2 from right. What does the b of x approach? Positive infinity. Okay. And what does this limit of x approach 2 from the left? The b of x is negative infinity. Okay. So what does this mean? Describing the function. So the same thing as you write if you are asked something like this in the test. So you will say this means you are given the limit notation regarding the behavior of from the left of the vertical asymptote and the right of the vertical asymptote. So this means that it is, or describing, we can write the same thing, describing the function approaching from left, because you see this negative here, that means from left, approaching from left, from the left side. As the x values approach approach 2, this is the left side of 2, approach 2 from the right. This is from the left. Our b of x approaches negative infinity. All right. I think it's as simple as how you describe. So meaning you are asked to describe, then you say as the function approaching from the right side, because you see that positive sign. As the x value approach 2 from right, the b of x approach the positive infinity. So you have to look at where the function approach to, whether it's positive or negative infinity. Okay, let's do some kind of question right here. You are asked to find the domain and the vertical asymptote of the following rational function. So when we say domain, we have taken this up. Where are we going to look at? We look at in the denominator. Okay, we look at the denominator. Our denominator here in the first one, f of x equals x times x plus 2 over x squared minus 4. We have a sum and difference of two terms here. So we could say x factor of 4 is 2. So this is x minus 2. We can cancel out. There is a hole in this. Oops, I canceled the wrong one. Okay, I can do this. So there is a hole when x equals 2. Now, what do you think our domain would be? How the line would look like? This is 0. If I substitute x plus 2 and x minus 2 equals 0, I have a value of x2 and x negative 2, right? So I have a positive 2 here, negative 2, and to the left is negative infinity, and to the right it's positive infinity. That is how you're going to look at when you write your domain. So your domain is the interval from negative infinity to negative 2, and or union with from negative 2 to positive 2, and union with 2 to positive infinity. So you try to make a sketch how it goes in the in the situation in the x, or where the domain is located. Okay, so what is our vertical asymptote? Vertical asymptote can be found in the denominator, all right? So that means we have only x minus 2. That means x minus 2 there. X is equals to 2. This is our vertical asymptotes. All right. B, g of t is t squared plus 4t minus 12 over t minus 2 squared. So we have, if we try to factor out the 2, we have t minus 2 and t minus 2. Multiplicity of 2. Well, the numerator, we'll try to factor out the numerator. So the factor there at it's 12. So t plus 6 and t minus 2 as the factor. So we can see whole at t equals 2. There's a hole. But there is t minus 2 still. So there is no hole. Right? So the domain. So we have the denominator t equals 2. That means when we look at the x, we're looking at 2 only. Okay, so this is the negative infinity and the right infinity. Since there is no other vertical asymptote here, only at that point. So that means our domain will be negative infinity and 2 union with 2 and positive infinity. So where is our asymptote located? We have to look at it in the denominator. T is equals to 2. That means our asymptote is where 2 is located in the x-axis. All right, let's do this. H of x is x cubed minus 3x squared over x squared plus 8x plus 15. What is common? Okay, let's factor out the denominator first, because domain and vertical asymptote can be found in the denominator. 15 can be factored out as 3 and 5. All positive, no problem with the sign. All right. So in other words, let's check if there are some holes here. X squared is common. Then we have x minus 3. All right. There is no hole. All right. There is no common. So if I draw in other words, our x here, if we equate this to 0, x is negative 3 and x is negative 5. Okay, so we are trying to find the domain. This is negative 3, this is negative 5, this is negative infinity right here, and the right is positive infinity. So let's start. We have 1, 2, 3 intervals here. So we can have negative infinity to negative 5 first interval, union with from negative 5 to negative 3, union with from negative 3 to positive infinity. Where is our vertical asymptote located here? So we have 2 vertical asymptote when x is at negative 3 and x at negative 5. So we have 2 vertical asymptotes. Okay. Let's have a graph. This is something like the more we can understand the limit notation here. All right. You're asked state the vertical asymptote of the following rational function, but this time you use the limit notation. Okay. So we can see here. I can make this bigger. So there is a vertical asymptote at x equals negative 2. All right. This is to the left of the vertical asymptote. This one right here. Left. And this is the right of the vertical asymptote. So this is the positive and this is the negative. If you try to look at that. Okay. So start writing. The first thing you do is to set up your limit notation. So the limit as x approaches, what is your vertical asymptote? Negative 2. I will write VA, vertical asymptote. From the left, so I'm doing from the left. What happened to the function here? Isn't it from the left, it goes up, up. Okay, that means it's positive infinity. Okay, let's set up from the right. Negative 2 from the right. This is the right, so at the right side, the function of x, look at the vertical asymptote, it goes down. So the function of x approach to negative infinity or equals to negative infinity. That is how you look at it. The left side and the right side as it approaches to negative 2. Okay, let's look at this graph right here. Let's find first the, okay, I think there is a sketch here for the vertical asymptote here. You can have it here. This is x equals negative 1. Let me start with this because there are two. Okay, one is right here at x equals 1. So I'm going to start with writing down the limit notation. Limit as x approach negative 1. Left, from the left. What happened to the function? Left of negative 1, this is the left of negative 1. This is the right of negative 1. So in the left of negative 1, look at the direction. It goes up, right? That means the function is equals to positive infinity. If we write the limit as x approach, I have the wrong notation here, sorry for that. X approach negative 1 from the left. So limit as x approach negative 1 from right. From right of here, it goes down. Okay, so that means it's equals to negative infinity. Okay, let's do the other asymptote. The limit as x approach 1 from left. What is the function? So in this case, this is the right and the left of 1. So the left of 1, what is happening here? The curve is negative infinity. It goes down. Well, the limit as x approach 1 from right, the function of x is, look at this, it goes up. So it's positive infinity. All right. I hope this is somewhat clear at this time, how you write your limit notation. Let's have the last figure. All right. Let's look at where we can draw our vertical asymptote here. right here. X equals -2. We have, okay, we can have here. I'm gonna make this bigger. So at X equals 3. So we have two vertical asymptotes here. At X equals -2 and X equals 3. Okay, let's write down our limit. So I'll start writing down. This is the left and this is the right of -2. This is the left and this is the right of +3. So as X approaches -2 from left, the function of X. So let's look at from left. The function of X goes down. It's negative, the curve down. Okay? Limit as X approach -2 from right. So where is from right here? It goes up. Right? So it's positive infinity, negative infinity here. So the function of X is positive infinity. Let's look at the other one. As X approaches 3 from left, the function of X. So let's look at the left of 3. It's going up, right? So that means the function is positive. The limit as X approaches 3 from right, the function of X. Look at the right of 3. It's going up. That means it approaches to positive or equals to positive infinity. That is how the graph goes. All right, let's do this. Oh, I think I repeated the same question. Let me check. I think I made this question already here. This is question number 2. All right, I don't need to do question number 5. I had it in question number 2 already. So we're done. All right, we're done. So I'm gonna do more vertical asymptotes in problems and solutions, so that you can review about it. And this, I can say that if I can do it, so can you. Don't forget to hit the like button and the subscribe button. See you in my next video.